lights up mean we're starting? Hello, world. This is CS50. My name is David Malan.
I'm Brian Yu.
And we'll keep this short since you might have done this already 3 times. But we are here in the afternoon of a filming of CS50's next course, CS50's Introduction. CS50's Fundamentals of Artificial Intelligence with CS50's own Brian Yu. I'm going to be behind the scenes on the chat. If you have any questions during this shoot, odds are we will start and stop a few times just to make some fixes. But if you have any questions, do ask them in the chat. I'll try to answer, and I'll also relay some of the questions if I can to Brian. Brian, as a teaser, what lies ahead?
Yeah, today we're looking at how AI can perceive the world using sensory-like input like you and I. We see the world, we hear the world, and we're going to be looking at how AI can do the same.
All right, thank you. This is CS50.
Welcome back, everyone, to Fundamentals of Artificial Intelligence. Now, so far in this class, we've been exploring artificial intelligence. We've been looking at ways we can give computers data and information and ask it to make decisions based on that information. We've given it the rules of a game and had the AI figure out what the right move is to make in that game. Or we've given the AI some numerical data and asked it to learn from that data to either analyze it, find clusters, make predictions, and that type of thing. Today, what we're going to ask AI to do is to perceive the world, kind of like we perceive the world through our senses. You and I experience the world by looking at the world with our eyes. We can see things visually. We can hear things with our ears and listen to sounds and process those sounds. And what we'd like to do is for AI to be able to do the same thing, to be able to use visual representations of data, auditory representations of data, and figure out how to use that to draw inferences, make predictions, and understand the world around it. So let's start by thinking about how AI can look at visual information and how computers process visual information a little bit more generally. So right here is a picture of our little AI duck here. You've probably seen it throughout the course a couple of times. And this really is just a picture on a computer screen. And you can imagine what would happen if we were to really zoom in on this picture and figure out what is this picture made of. We'll zoom in on it. And what you can probably start to see as we really zoom into this picture is that from a computer's perspective, each picture is really just made up of these individual pixels, these square dots on this grid of pixels that exist here, where each one has a different color. And all taken together when viewed from afar, it really looks like something. But in terms of the data the computer is actually storing about any given image, it's really just these individual pixels that have some color. So let's dive into that pixel and see what might that pixel be represented as inside of the computer. We'll start for now with just black and white and shades of gray. We'll get back to color a little bit later. But each pixel, for now, you can think of as really being represented just by a number. Maybe the number 0 will be all black, and maybe the number 1 will be all white. And then some number in between is going to be some shade of gray in between, where the higher numbers are going to be closer to white, the lower numbers are going to be closer to black. So a number like 0.5, that's kind of somewhere right in between white and black. It might be a shade of gray that looks a little something like this. If we decrease that number even further, a number like 0.25, now it's a little bit darker, a little bit closer to black. So for now, think of each pixel as just being a number, where that number represents how bright or dark that pixel is. 0 means very dark, like black. 1 is going to mean very light, like the color white. And so by assembling pixels that look something like this, just these numbers all together, we can start to form pictures that we might want a computer to be able to look at and analyze. For example, you might want to give an AI a picture of an animal and ask the AI to identify what kind of animal is it. Or if it's a picture of something else, like a picture of a chair, for example, or a computer, we might want the AI to be able to detect what that is a picture of. Now, one of the earliest areas where computer scientists started with thinking about how AI can understand images was through the problem of handwriting recognition. The idea that if you were writing something on a sheet of paper, a letter or a number, for example, could the AI figure out what letter or number you wrote down? And that has lots of different applications. For example, the mail service might be really interested in that. If they could take an envelope and look at the envelope and have a computer process someone who had handwritten an address and a postal code, for example, to figure out what those characters are and where they need to route that particular envelope. And it turns out to be kind of a challenging problem. If you think about the way that we might write handwritten digits, I'll try and write like the number 2, for example. There are lots of ways I could do it. I could write the number 2, and sometimes it might be narrower, sometimes it might be wider. Some people will put a little loop in there too, for example. So different people will write the same digit in different ways, and even the same person with the same handwriting might end up writing the same digit a little bit differently every time. So it's not super obvious what it is that we need to look for. We need to understand something a little bit more general about the patterns we're looking for in order to figure out how is it that we're going to try and understand handwritten digits. So the example we're going to look at now is all about how computers can try and understand these digits, but know that that idea is going to apply to really any kind of image that a computer might try to understand. If we're looking at a photograph of something, we would want to understand what the different parts of it are to figure out what it's a photo of and potentially make a decision based on that. So let's take a look at what a handwritten digit might look like from the perspective of a computer and start to think about how it is we might start to analyze that information. So right here is a 4x4 grid of pixels, and what I've drawn in this 4x4 grid of pixels is what you can hopefully notice as the number 4. It's a representation of the number 4, and each one of these pixels, recall, is just a numerical value in this case, where 0 means very dark, 1 means very light. So I can show you what those numerical values look like. So 0.99, for example, is very light, and 0.16 is very dark. And of course, if you're looking at a photo, it's not going to be perfect. Not all the pixel values are going to be exactly the same. Sometimes someone's going to write darker with their pen or pencil, or lighter in other cases. And so these numbers you can see is generally the shape of the number 4, but not all the pixel values are perfect. It's not exact in terms of what it looks like. So you and I can look at something like this, and hopefully we can see that that definitely looks like the number 4 in this case. But what is the computer really seeing? The computer is really just seeing the numbers. So if I took away the shading and I just showed you the numbers, this is really what the computer is seeing when it's getting a particular image, when it's looking at a handwritten digit and trying to figure out what it is. And if I just showed you this, how easy or difficult would it be for you to determine that this is, in fact, the number 4? Well, we'd have to start looking at it a little bit more closely. And there are some things that you might try to pay attention to. One thing you might try to pay attention to is when things change from a smaller value to a bigger value. That you notice, like, here's a small value, 0.16 here, a bigger value, 0.92 here, and then a smaller value, 0.24 there. And there's something similar going on here with 2 smaller values and a bigger value in between. That kind of thing might be representative of like a line. Like you've got a line of lighter pixels here with darker pixels on either side. And you can start to notice that in particular regions of this 4x4 grid, you can try and spot some of those shapes. Maybe you'll notice that, oh, there's probably a line here. We have some lighter pixels along that way and some lighter pixels here. And by understanding those individual parts, you can start to piece them together and figure out, all right, maybe this is in fact the number 4. And so what we want ultimately is for computers to be able to engage in a similar kind of process, to be able to take all of this just raw pixel data, figure out in little pieces what particular parts of the image might represent, and then figure out how to put all of that information together to ultimately arrive at the conclusion that this is what the particular handwritten digit happens to be. And so what we're trying to solve is ultimately a classification problem. We talked about classification earlier in the course, the idea that we're giving the computer some data, and we want the computer to assign that data to a category. Before, we were trying to categorize natural data information as, like, is it a rainy day or a not rainy day? In this case, what we're trying to do is take handwritten image data and then convert it into one of 10 categories. What handwritten digit is it? Is it a 0, a 1, 2, 3, 4, 5, 6, 7, 8, or 9? Those are the categories that we're trying to group our data into. And so it's a classification problem. Now, how did we solve classification problems before? Well, we had a few different options, but one option that proved pretty useful was the neural network. where we had a layer of input units where we provided numbers as input to this neural network. And then we had some output predicting in maybe one of 3 categories, or in our case, one of 10 categories. And then we had connections between these units of the neural network that allowed us to try and calculate, based on the input, what the correct value for the output should be. And what the neural network was learning, you'll recall, was these individual weights, the values of these connections between units in the input layer and units in the output layer that allowed the computer to pretty accurately figure out how to take that input and transform it into an output. So what would it look like if we tried to use a neural network like that to try and solve the problem of handwritten digit recognition, at least in our case? Well, we can think about what are the inputs to our problem and what are the outputs to our problem. The input was that 4x4 grid of pixels that we had. And so we can think about, well, how many values is that really? Well, if we have a 4x4 grid of pixels, and each pixel for now is just storing a single numeric value, then we have 16 inputs, 4 times 4, for 16 pixels in our image. So instead of this neural network here, if we wanted to design a neural network to work with 4x4 images, we would need 16 inputs. So here we'll have 16 inputs, 1 for each of the pixels in our 4x4 grid. And then how many outputs do we need? Well, the output of our classification neural network is going to be 1 unit for each of the different classes, each of the different things we might be trying to categorize. So 0, 1, 2, 3, 4, et cetera. There are 10 different digits, and so we need 10 different output units. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different output units. And now what we need are connections between them. So you could imagine drawing a connection from each and every one of these input units to each of those 10 output units over there. And what you can start to see is that there are a lot of connections going on here. If we were to try to train a neural network like this, there would be a lot of weights that the computer is ultimately going to need to learn to figure out how to transform this input into that output. And even then, that's assuming that the input we're dealing with is a 4x4 grid of pixels. In reality, a handwritten digit might be represented as many more than that. There's a famous data set of handwritten digits called the MNIST data set of handwritten digits, and they represent images as a 28 by 28 grid of pixels. And so this is many more, close to 800 different pixels, and therefore would be that many more inputs that would have to go as input to that neural network as well. Gonna get some water, and then I'll pick up from there. So what we can see from this is that images have a lot of data. In a 28 by 28 grid of pixels, that's going to be a lot of inputs into our neural network. And so we're going to have to think carefully about how we're going to construct a machine learning model that's going to be able to deal with that well. And this is where we can start talking about a domain known as deep learning. The idea behind deep learning is that we're building these multi-layer neural networks. Instead of just one input layer and one output layer, often deep learning networks will have many, many layers, where each layer is responsible for just doing a little bit of additional processing to help us transform the input to the output. And it's particularly designed for figuring out how to deal with large data like images or sounds or the like, for example. And so what a deep learning network might look like is we have multiple layers. And then the units in each of those layers might be connected to each other. So we have this input layer over here, we have an output layer over here, and then in between, in this case, we have 2 hidden layers, but there might be more hidden layers than that, where there are connections between each layer and the layer that comes after it. And so the goal then is going to be to figure out how are we going to construct those layers intelligently to help us deal with particular different kinds of data. Because the kind of ways that we might want to construct a layer for image data might look different from how we're going to construct a layer for dealing with other kinds of data instead. And so we're going to be trying to create these multi-layer neural networks, and we'll get into details in just a moment as to what those layers look like. But oftentimes, it's going to be helpful for us not to think about these layers in terms of individual units anymore, just because we're going to start be dealing with much larger layers. Instead, you'll often see me represent them just as these individual blocks with arrows going between them, where we have an input layer being transformed into a hidden layer, and then another hidden layer, and then the output layer, for example. And so data is going to flow from beginning to end, hopefully being transformed and processed in a way that's going to be helpful. And so what kind of processing would be helpful for us when trying to understand handwritten digits? Well, let's go back to the handwritten digits I was just drawing a moment ago and think about, what would we need to understand about these to be able to identify that they're all the number 2, for example, or they were all the number 4, for example, to understand what digit it is. And remember that if the computer is just starting by looking at individual pixels, then at first, the best you could probably do is try and understand relationships between a couple of pixels that are near each other. Maybe you could identify one of these curves here at the top of the 2, or something straight near the end of the 2, identifying the tail, for example. And once you identified those smaller pieces, then you could imagine trying to combine those pieces together in order to understand larger and larger concepts. And that's going to be one of the ideas behind these multi-layer neural networks, is that we start at the input layer with just pixel data, and then as we go layer by layer, we can start to develop an understanding for more and more complex features. At first, the features in the early layers might just be small things like an arc here and a straight line there, and then over time, we can start to combine them to form more sophisticated features that will help us to really identify what digit is really here. So as an example, if I have 4 layers here from input, 2 hidden layers, and an output, in the first layer, we might just be able to identify, here are some individual pixels. We could use those pixels to maybe then start to understand lines that might be at a particular angle, for example, or to identify the length of particular lines. And then you could imagine trying to combine those lines together to form particular shapes that are made up from multiple lines together. So one hidden layer might be responsible for that. And then afterwards, we could try to combine some of those shapes to identify what the handwritten digit really is. And this is a bit of an oversimplification. This is what a neural network might be looking at. But a neural network might have many hidden layers with many different units. And it's not always obvious what those units are actually doing. This is an open problem in the world of artificial intelligence, which is this problem of the understandability of the machine learning models that we create. We can often create models that do a really good job at performing some task, like figuring out what a handwritten digit is, but then being able to really understand how exactly the model figured that out, why it chose the particular weights that it did, or why it chose to represent particular units in a certain way, that's often a more difficult question for us to be able to answer. And it's one that we'll be thinking about as we continue to try to design these machine learning models. So what exactly could a computer do if we were going to try and construct a layer that would be able to take an image and be able to analyze that image? Well, let's take a look at an image. Here's an image just of a square, for example. And this right now is like a perfect image with perfect pixel values. We've got, ones, really bright pixels that are making up the square, and then zeros that are making up the entirety of the background. In reality, pixels are not going to be that perfect. If you really took a photo of something that was a square, it might look a little something more like this, where not all the pixel values are the same, but there's still definitely a square here. And so if you were to try to train a computer to be able to identify relevant pixels in this image, to be able to try to understand what this is an image of, well, how could we do it? We could try taking in all of the pixels at once, but that's a lot of information to try to deal with all at once. And so often what we'll do is we'll try and focus on just one part of an image at a time. Like just focus on the upper left corner of the image, or just focus on the upper right corner of the image, and do that across the entire image. Because odds are, the pixel values in one part of an image in one particular pixel, those are probably pretty relevant to the pixels that are nearby. Like we care about understanding these 2 pixels together, and maybe don't care so much about the relationship between this pixel and that pixel all the way down there in the lower right. And so the idea is going to be that we're going to look at a particular window of this image. Maybe we're going to start with this upper left 3x3 grid of pixels, and we're going to try and analyze that particular 3x3 window in some way. and we'll talk in a moment about how exactly that's going to happen. But then we're going to slide this window over and do the same thing for the next 3 by 3 region of the image that's right there. And then after that, we'll slide the window over, do the same thing for the next 3 by 3 window, so on and so forth, going through this entire row, just looking at 3 by 3 windows sliding across the image. And then we'll do the same thing for the next row. We'll bring this window over here, look at this 3 by 3 image, then look at the next 3 by 3 region, so on and so forth, going through the entirety of that second row. Then we'll move on to the third row, do the same thing. Then the fourth row, process that whole line. Then the fifth row, process the line after that. So the idea is going to be that rather than look at the entire image all at once, by focusing on smaller regions of the image, like a 3 by 3 grid of pixels, hopefully we'll be able to extract some useful information from that, to be able to figure out what's going on in that 3 by 3 region. And if we understand what's happening in every 3 by 3 region across the entire image, then hopefully we'll be able to draw some conclusions from that, figure out something useful that our neural network will eventually be able to use to make some conclusions about this particular image and what's inside of it. Sorry, let me check what's coming next. So now we have this idea that we're going to be sliding this window across the image, studying a 3 by 3 grid of pixels each time. But now we need to figure out what actually is that processing going to look like. If we have some 3 by 3 grid of pixels, what are we going to do to it to analyze it, find out some useful information about it? And so let's take an example. Let's focus on this 3 by 3 grid of pixels at around the middle of the image. And what might we want to figure out about this particular grid of pixels? Well, what I might be interested in knowing in this case is that there seems to be some kind of an edge here, that we go from darker pixels here to lighter pixels beneath that. And so what I want to do is a little bit of edge detection to be able to take the image and have the computer figure out that there is, in fact, an edge here between darker pixels and lighter pixels. So how am I going to do that? I'm going to use what's called a convolution, which is a little bit of a fancy term, but I'll explain what it means right now. What it means is we're going to process this 3 by 3 region with a set of values that we're going to call a kernel. And this is the kernel we're going to use. And I'll show you how to interpret this kernel. This kernel is also a 3 by 3 grid of values that sort of maps onto the 3 by 3 grid of pixels that we have here. And what we're going to do is essentially multiply each value in this 3 by 3 grid of pixels that we're focusing on in our window by the corresponding value in the kernel. And then we're going to add all of those values together. So we have this pixel value, 0.11. We're going to multiply that by -1. Then we're going to take this pixel value, 0.07, multiply that by -1, 0.10, multiply that by -1. And then all these 3 values in the middle, those are going to get multiplied by 0. They'll just end up being 0. And then these 3 in the bottom, those are getting multiplied by 1, meaning they're pretty much staying the same. And so then we're going to add all of those values together and figure out what the sum is. And so if you do that, multiply all these by -1, multiply all these by 0, multiply all of these by 1, add all those values together, what you end up getting is some positive value. And why would you get a positive value? Well, we took these relatively large numbers, multiplied them by 1. And then these negative ones essentially act as like subtracting. So we're subtracting away these relatively small values over here. And so what we end up with is a positive value. And this positive value in this case is telling us something. It's telling us that it seems like the pixels here at the bottom are brighter or have a higher value than the pixels that are over here at the top. I can show you what that would look like in a different region of the image too. Imagine we look now at this region of the image where all the pixels are pretty bright, and we applied exactly the same kernel with -1s in the first row, 0s in the second row, and then +1s in the third row. We do the same thing. We multiply each of these by -1. We multiply each of these values by 0 in the second row. We multiply each of these 3 values by +1, and we add up all of those values together. And what we get is a number pretty close to 0. And that might be kind of what we expected, that if all of these values are pretty similar, then if you add up 3 positive versions of all of those values, and you subtract 3 negative versions of all of those values, then the result is probably going to be pretty close to 0. And what a number pretty close to 0 tells us in this case is that there doesn't seem to be an edge in the vertical direction going from up to down. They're actually all pretty similar in terms of their values. And so what this kernel allows us to do is compute this convolution, multiplying these values together, adding them all up, and getting some value as a result. And that's telling us something useful about this part of the image. It tells us whether or not there is an edge going in one direction or another. And this isn't the only kernel we could have used. We could come up with other kernels too. For example, if I take the same kernel and I rotate it a little bit so that it's going -1s in this first column, then 0s, then 1 after that, well, that's also going to be doing some edge detection, but it's going to be looking for edge detections in the other direction, in the horizontal left to right direction, because we're going to be looking at what are the values of the pixels in this column compared to the values of the pixels in that column. And so if we applied that same convolution with this new kernel, what we're going to get is also a number that's fairly small. It doesn't seem like there's really an edge or a boundary going from left to right in this 3 by 3 window of the image. Whereas if we did the same thing in this 3 by 3 region of the image, over here on the left side of the image, take each of the values in this column, multiply them by -1, take each of the values here, multiply them by 0, take each of the values in this third column, multiply them by 1, add up all of those values together, we end up getting, once again, a larger value, demonstrating that there does seem to be some kind of a border here between the darker pixels on the left side and then the lighter pixels on the right side. So let's give this a try across the entire image with a different matrix, filter matrix here. here's the filter that we're going to be using, or kernel. You can kind of use those terms interchangeably. And what we're doing here is we're taking the center pixel, the middle of this 3 by 3 grid, multiplying it by 8, and then multiplying all of the other pixels by -1 and adding them together. And let's think for a moment and see if we can figure out what might that be doing for us. Well, imagine what would happen if all of the pixels had pretty similar values. If they all had pretty similar values, we're going to take the value, multiply it by 8, and then we're going to subtract 8 instances of it for all of the 8 pixels that appear around it in that 3 by 3 grid. And so you should end up with a number that's pretty close to 0 if all of the pixels are pretty similar. But if this middle pixel has a much larger value than some or all of the pixels that are around it, well, then we're probably going to get some kind of positive value as a result of it. So what this kernel is telling us is it's essentially a way to determine if there are edges in any direction in the image. We're comparing the center of this 3 by 3 grid to all of the pixels around it to see if it's similar or different to those pixels. So if we apply this convolution here in this upper left portion of the image, we're going to get some particular value, in this case -1.68. And we can slide this window over and do the same process on this 3 by 3 part of the image here. We'll get a different value, and we can repeat the same process. Do it here, get a new value, do it with this set of 3 by 3 pixels, get a fourth value, and do the same thing to finish off that first row. We get one more value. And then we'll do the same thing for the next row of the image. We'll look at this 3 by 3 grid of pixels, and this time we get a fairly positive value. We're taking a pretty big value, multiplying it by 8, and then subtracting away all of the pixels that are around it. But because this is a fairly large value, we're getting a pretty big value as a result too. We can do the same thing, continuing through the row. We'll see what happens. So at the end of it here, this is a pretty small value. When we multiply it by 8, subtract away the ones at the edge, we're going to end up with a smaller negative value in this case, because we're subtracting some fairly large values here. Let's try the next row and see what happens. We'll apply the convolution to this 3 by 3 grid of pixels here. Then what will happen when we do it here, where all of the pixel values are, again, fairly bright. They're pretty large values, and they're all pretty similar to each other. We're going to multiply the middle one by 8, subtract away these 8 that happen to be around the edge. And the end result of that is we'll get a pretty small number as a result of it. We'll do the same thing here, keep going all through the rest of that row. And then we'll do it here with this fourth row. Again, this is a pretty small value because all these values are pretty similar to each other. We'll do the same thing and finish off that fourth row. And then finally, we'll do this one last time with one more row, looking at the bottom left, this 3 by 3 grid of pixels, performing that convolution, figuring out what the resulting value is. Again, it's fairly large because we have one bright pixel surrounded by some darker pixels here. We'll do that again here, then with the middle of the bottom, and then 2 more times, once with this 3 by 3 grid, and then finally we'll finish it off with this bottom right section. And what you're noticing as a result of this is that we've transformed our original image into this version of the image. And this version of the image over here is what we might call a feature map. It's the result of applying the same convolution across the entire image, and hopefully that convolution is going to tell us something useful. In this case, the convolution was hoping to tell us something about where the edges or boundaries of the image are. And so while we started with this solid square part of the image here, what we ended up with was a filter map that told us approximately where the borders of that square are. So it gave us a little bit of ability to detect the edges of that image in order to understand that image a little bit better. And so that was just one possible filter we could have used for processing that image, understanding what's in that image by applying a particular 3 by 3 kernel across each of the 3 by 3 regions of the original image. But there are potentially many other kernels we could have used to filter and process the image in different ways. Maybe you're looking for lines in a particular direction, or you're looking for particular angles, for example, or particular shapes. And you can imagine having different kinds of kernels that are performing different kinds of analysis ultimately on that image. And so let's come back now to the idea that we want to take that idea and put it into a neural network. That so far, when we've been thinking about neural networks, we've had this layer of units, we've had another layer of units, and then we've connected each of the input units to each of the output units. And this is what we might call a fully connected layer of a neural network. So far, when we've been designing neural networks, all of our layers have been fully connected because every single one of the inputs is connected to every single one of the outputs. This input here has 3 connections for each of the 3 outputs, and that's true for each of the inputs here. And for each of the outputs, they have 4 incoming connections from each of the 4 inputs that are here as well. Now, if we were going to apply this and try and bring it into an image, we might not want it to be fully connected. We might not want every single input to be connected to every single output, because in an image, usually it's only particular regions of the image that are related to each other. That the upper left part of the image might not have that much to do with the lower right part of the image. And as a result, we might want to consider just pixels that are located near each other as relevant for analysis first, before considering how all the parts of the image really relate to each other. Take a short break, and then I'll continue from there. So for processing images, instead of using a fully connected layer, we're going to use a different kind of layer, a layer that takes advantage of these convolution filters that we were just talking about trying to apply to an image. And this is going to be a particular type of layer called a convolutional layer. So how is that layer going to work? Well, in a traditional fully connected layer, we had a bunch of units, we had another layer that it was connected to, and then we had connections between each of the input units and each of the output units that were performing some kind of a calculation. And then we were learning the weights of those connections to figure out how to transform the input into the output. In the case of a convolutional layer, the input we're going to think of, in this case, as a grid of pixels. The convolutional layer will literally take this grid of pixels as input, and then the weights between it will essentially be, instead of multiplying each of these pixels by a particular weight and having different ones for each of the possible outputs that it could eventually transform into, we're just going to apply a convolution. We're going to apply one of these 3 by 3, or you could define a different size if you wanted to, but in this case, a 3 by 3 kernel, apply a convolution, and as a result of that, we'll get a different sequence of values, one of those feature maps that we were looking at a little bit before. And so we're starting with the image, applying a 3x3 convolution like the one that we've seen before, ending up with a different feature map describing the result of applying all of these filters to each of the regions of this image as we slide a particular window across that image. And what's important here is that when we're designing this convolutional layer, we're not telling the computer exactly what convolution to be performing here. We're not specifying what the values of this kernel should be. We looked at a couple that might be useful with like the 8 in the middle and the negative ones around it for detecting edges in any direction, or different ones for detecting edges horizontally or vertically. What we're going to do is just treat these as values that the computer can update as needed during the training process. In the same way that when we designed a neural network with connections between the inputs and outputs, we didn't tell the computer exactly what values to use for each one of those connections. In this case, we're not going to tell the computer what values to use for this filter. We're just going to let the computer figure it out on its own via the use of training data. And so as we give the computer more and more data, what we're going to learn via the machine learning process is what filter we should be applying in order to best allow the computer to be able to predict the output from the input. Maybe that'll look like edge detection, maybe that'll look like something else, but ultimately it's going to be something that the computer will find helpful for being able to perform this transformation and do something like predict handwritten digits or predict what animal it sees in a photograph, for example. Now, in practice, it might be useful for a computer to apply not just one filter, but multiple filters. Remember, we had one filter that looked for edges in the horizontal direction and one that looked for edges in the vertical direction. Maybe a computer would like to do that too, or maybe they'd like one filter that's looking for one particular kind of angle and one filter that's looking for a different kind of angle instead. And so instead of just applying one filter and ending up with one feature map, we can do this multiple times. We can apply multiple convolution filters to the same grid of pixels and end up with multiple different feature maps that we can then combine later in order to figure out how to deal with them and figure out how to process them and turn them into something that will be useful for our neural network to be able to then understand. And so these convolution layers are going to allow the computer to just look at individual regions of the image, use them to make predictions. But the nice thing is we have far fewer weights that we need to worry about. Remember before when we were trying to connect all of the input pixels to all of the possible output units, we had many, many different connections that we were ultimately trying to learn, meaning many, many values that we needed to learn instead. In this case, we're using the same set of values, just all of the values that happen to be in this particular kernel, and we're applying them across the entire image, repeating or sharing those same weights as we process the image one row at a time. And that's going to allow us to be able to learn a little bit more quickly. There are fewer values the computer has to learn, and as a result, hopefully we'll be able to learn them a little bit more quickly. So that's the idea behind a convolutional layer. The idea that we're starting with this image, we're applying a convolution, and then ending up with some feature maps, and the computer is going to figure out what kind of convolution to perform in order to best allow it to predict some output from some input. But there are some other types of layers that might be useful for us to take a look at too. In particular, let's try and look at the example of a pooling layer, another layer that's pretty common when we're trying to deal with images.
If you want to pause, we have a camera issue anyway.
OK, yeah, pause then. So a convolutional layer is going to allow us to perform calculations like this. Start with an image, figure out what kind of filters we would need in order to get some feature maps that our computer is going to be able to use to infer what that picture is a picture of, for example. But that's not the only type of layer that can be useful when trying to deal with image processing. Another one we'll take a look at is one called the pooling layer. So what is the idea behind a pooling layer? Well, an image has a lot of pixels in different places, and ultimately, it's a lot of information. We might like to reduce that information to less information to be able to really capture what's important in different parts of that image. So for example, if we go back to my handwritten 2s here, we might care about knowing that at the top of the 2, there's this tip of the 2 here at this edge, there's the tip of the 2 here, there's the tip of the 2 here. But if we were to map all of these to individual pixels, in a grid of pixels, those tips of each of the shapes are probably going to show up at different pixel values, right? It's not exactly in a particular pixel that you're always going to find this part of the 2, but it's probably in a general area of the image where I'll find this particular part of the 2. And that's one thing a pooling layer can help with. It takes a big image, turns it into a smaller image by combining data from across different pixels. And so what might that look like? We'll take a look at an example. Here is a 6x6 grid of pixels representing the number 4. And what I'd like to do is reduce that down to a smaller image by pooling some of the pixels together. And so how could I do that? One common way to do this is via what's known as max pooling, where I take a bunch of pixels and I pick the pixel with the largest value as the one that I want to use. So I might start with this 2x2 grid of pixels here. And I'll pick the one with the largest value. In this case, that's a 0.89. That's the one with the biggest value. So in my resulting image, my pooled image, I'm going to use that pixel value, 0.89. So we see a 0.89 here as the result of that pooling. Then I'll slide the window over to the next separate set of 2x2 pixels, this set of 4 here. And in this case, the largest pixel value is this 0.12 that happens to be right there. So we'll go ahead and add 0.12 to the result of my pooling. We'll do the same thing for the upper right. Here in this case, if I was going to do a max pooling operation, look for the largest pixel value. The largest one is the 0.85 here. So that one, that's going to go into the result too. And then I'll do the same thing as we move down the image. Now, if I look at this middle section of the image, pick the largest value, that's going to be the 0.92. That one's going to go into my pooled result. Same thing for the middle of the image. It looks like 0.88. That's the largest value. That's going to go into the result. Then over here, 0.93 seems to be the largest, so that one will go in. And then I'll do it one more time for the bottom of the image. Again, looking at each sequence of 2x2 pixels, picking the largest one and adding that to the result. So we'll look at that one there, and then finally look at the bottom right. And the result of this entire pooling operation is that I started with a 6x6 grid of pixels, so 36 different values, each representing how bright or dark that particular pixel is. And I was able to pool a bunch of the pixels together to get a 3x3 representation of the same thing. Only 9 values now, but I'm still able to capture the essence of what the original image was, which is it's an image of the number 4. And so this can be helpful as we have a lot of data in large images, just to be able to reduce the size of them and say that, you know, there's a line here in the upper left part of the image, but maybe I don't care so much as to whether it was this pixel or this pixel that was the tip of that 4, for example. I really just care that it was a particular area of the image where I found that particular feature of the handwritten digit in this case, or the object if you were trying to take a picture of an object and tell what that object is. So now we have two different ways of trying to process an image. We have a convolution, where we apply some filter to the image to be able to look for particular kinds of patterns. And we have pooling, where we can take a bigger image, turn it into something smaller by reducing the amount of data inside of it, by like picking the largest pixel value each time. Now what we're going to do is combine those two ideas to create a convolutional neural network, a neural network specifically designed for performing processing like this, particularly useful for things like image processing. The way a convolutional neural network is going to work is we'll start with our input. And our input might be a very large image, but the first step we're going to do is have a convolutional layer where we apply some kind of filter over the image to end up getting some feature map, some result of applying that convolution. And again, we might do that multiple times. So rather than just have one feature map, I might have multiple feature maps for different things that our neural network might want to pay attention to or filter for when taking the original image, processing it, and trying to generate some kind of a result. After we perform that convolutional layer, we'll typically then do a little bit of pooling. There's a lot of data here. We might want to just aggregate it together a little bit. We'll apply a pooling layer to get smaller versions of each of those filter maps, just to be a little bit easier for us to work with. And now there's no reason why we have to limit ourselves to just doing these things once. We can do them multiple times. We can apply another set of convolutional filters now on this result. We've pooled it together. We've been able to identify maybe some of the smaller features of the image. Now we want to combine those features to identify larger parts of the image. So maybe we'll add in another convolutional layer, generate some more feature maps by processing this original one, and then perform another pooling layer where we take the result of that convolution, shrink it down even more just so there's less data for us to work with, a little bit easier for us to process. And at the end of all of this, and we might repeat this multiple times further, we have much less data than we started with. We've been able to reduce things down, hopefully, to just a few values that are ultimately going to be useful. But then we can take that information and just put it into one of our normal feed-forward neural networks, where we take each of these values resulting from these convolution and pooling layers at the end, just turn them into individual units by flattening them out, and then pass them into a neural network that will then go ahead and perform some kind of classification, for example. In one case, it might be trying to figure out what handwritten digit was written. In another case, it might be looking at a picture of an animal and trying to tell us what kind of animal that was, for example. But all of that taken together is what our convolutional neural network might ultimately end up looking like. And so by combining these kinds of operations, we can do some processing on the image to figure out what the image might actually be. But there are a few things we haven't yet talked about that we do need to think a little bit about. So far, we've been assuming that every pixel is just one value on some range from all dark to all light. But in practice, when we're dealing with photos, often photos now are going to be in color. And so they're not just all black or all white or some shade of gray, but we have some color to it as well. And so instead of representing every pixel as just one value for how light or dark that pixel is, conventionally, we could also represent a pixel as three values. One value for how much red is in the image, one value for how much green is in the image, one value for how much blue is in that particular pixel in this case. And so they can range from a little bit of red to a lot of red, a little bit of green to a lot of green, and same goes for how much blue happens to be in that particular pixel. And so if we have all red, all green, all blue, that's going to be a pure white pixel. Meanwhile, we could change the amount of red, green, and blue to create different colors. And so depending on where we set the RGB values, R for red, G for green, B for blue, we can end up representing different colors to put together an image of something else. For example, we could put together the image of the duck that has different colors all being combined together in various different ways. And so how then would we have to adjust our algorithm for designing a convolutional neural network for working with pixels of different colors? Well, before, we assumed that our image was just one grid of pixel values like this, where we had one grid of values representing all of the values in the image. Now, this really might just be a grid of all of the red values of the image. But we're also separately going to have all of the green values for the image and all of the blue values for the image. And all of those taken together might be things that we need to look at when trying to process the image. And ultimately, we might want to deal with each of those colors separately. Imagine you're trying to design a neural network that can look at traffic lights and traffic signs and figure out what they're saying. In that case, it's probably pretty important to be able to process the red from the green from the blue differently, to be able to detect different kinds of colors and make different decisions based on what they are. So when we're applying a convolution to this kind of data, often what we'll do is we will have separate filters for each of these three different channels, so to speak. We have a red channel, a green channel, and a blue channel. Each one of them will be passed through a different convolutional filter. And what our neural network is going to learn is it's going to learn what kind of processing do I need to do on all of the red data in the image? What kind of processing do I need to do on all of the green data in the image? And likewise for all of the blue data, in order to transform that data into some feature maps corresponding to the red, green, and blue original parts of the image. And then the computer will eventually be able to combine all of those feature maps together. But you could imagine that each of these filters is going to be doing different things to be able to figure out how am I going to process that image in order to transform the input into the output, paying attention to the relevant colors to figure out how it needs to go about actually trying to combine all of that information. And so that's going to allow us to go from processing just black and white images to processing color images that might have red and green and blue across all of those different pixels. But what if we wanted to analyze not just images, but video? What's different when we go from images to video? Well, the dimensions of our data are now going to change a little bit. When we're dealing with images, images really have a height and a width, and that defines our grid of pixels that we have. But in the context of videos, we now have a duration. We have the duration, and for each moment in time, we have the height and the width. And you can measure the duration in seconds, but more conventionally, we'll represent the duration in terms of the number of frames of video. That video is often 24 frames per second, or 30 frames per second, or 60 frames per second. And for each one of those individual frames, we're going to have an image that we might like to analyze as a result of that. And it turns out we can use similar kinds of strategies. We used a convolutional neural network for analyzing images that looked at one part of the image and then slid a window over that image in order to look at different parts of the image to extract different features from it. We could do a similar thing for video too. Imagine that we had 5 frames of video, frame number 1, frame 2, frame 3, frame 4, and frame 5. We could analyze them in sequence by looking not just at a single 3x3 area. Sorry, I'll go back and do that part. Yeah, I'll go back from here. So let's take a look at how we could apply something similar to video as well. We could imagine that we had a video with 5 frames. Here's frame number 1, frame number 2, frame number 3, frame number 4, and frame number 5. And before, in a convolutional neural network, we would take, let's say, a 3 by 3 grid of pixels and then slide it over spatially the image, going over all of the rows and all of the columns of the length and width of the image. But now we have another dimension, which is the time, the duration of the video, frame 1, frame 2, frame 3. You can imagine constructing a 3-dimensional convolutional neural network, where instead of just looking at one 3 by 3 grid of pixels in one frame, we look at it across multiple frames of time. Maybe you're going to analyze 3 frames in sequence altogether. And so you could imagine having a filter that would apply to a 3 by 3 grid of pixels across 3 different frames in order to analyze potentially whether there was motion between one frame and the next frame, for example, in the same way that you could try to look for edges or boundaries spatially in an image, like there was a lighter pixel on the left and a darker pixel on the right. You could imagine doing something similar across time too, that if pixels are a certain color in an earlier frame and then they change color a few frames later, then probably there was some kind of motion or some kind of change happening that you might want to pay attention to across those particular frames. And then in the same way that spatially, we could slide a window across the image, across the rows, and across the columns of the image, we can slide this filter across time in the video, that if these are the frames of video, you could then slide over and now consider analyzing the top left of the image across the next sequence of 3 frames of the video, and then the sequence of 3 frames in the video after that. So we can extend this idea into multiple different dimensions to use convolutional neural networks for a wide range of possible purposes. So now let's talk a little bit about how, in general, we go about trying to train a neural network like this. What is the training process like? How are we organizing the data in order to figure out how to actually get a neural network to be good at doing tasks like this? Well, what you imagine is, let's say here's a neural network for processing images. In reality, it'd probably be much bigger than this, many more inputs, many more outputs, many hidden layers in between it. But this is a simplified representation, at least for now. And as input to the neural network, we might give it, say, an image of a handwritten digit, like an image of the handwritten digit 2. We'd run it through the neural network, and at the end of it, it would predict a classification. It would predict what handwritten digit do I think this is, and we hope that it's going to predict the number 2. But of course, that's not always going to be the case. Sometimes it's going to get it wrong. So if we provide it with this digit, for example, you and I can probably look at this and see that's probably the digit 8. We've got the loop on top and the loop on the bottom. But if we fed it through the neural network, sometimes it might get it wrong. Maybe in this case, it predicts that the number is in fact a 6. And at that point, we have the ability to learn from that process, to be able to go back and say, how do I need to adjust the weights in this fully connected layer to be able to figure out how to get it to be more accurate in the future? Or if I'm looking at convolutional layers, how do I need to adjust the values in the filter for what I'm filtering for to hopefully allow my neural network to be more effective at trying to predict output based on input? But once you've trained the neural network, how do you know how good or bad it is as a result? Well, what you need to do is test the neural network that you've trained. And the best way to test it is you might start by training your neural network on a whole bunch of data. So here's a whole bunch of handwritten digits from the MNIST data set. But then when you test it, when you're trying to evaluate whether it was good or bad, what you want to do is give the neural network an image that it hasn't seen before, some new image that wasn't in any of the original training data, because the original training data your computer has seen before, it's learned from, it's tried to memorize potentially. What you want the computer to do is try now to generalize, to be able to understand what a 5 looks like, and not just what this particular 5 looks like. And we'll test it to see how well it does as a result. So what might that look like? If you have a whole bunch of data, often what we'll do in the neural network training process is we'll split up that data into different groups. We'll split it up into a training set and a testing set. The training set is the data that we're going to train on. We're going to show data to the neural network, allow it to learn from it, figure out how to identify patterns in the data that it's seen before. And then the test set is a set of images that it's never seen before, something that we can test the AI on later in order to evaluate whether it really learned well from this original training data. And often, we'll see that you can split the data into a third set too, called a validation set, which you check against when making changes to the neural network. But the important thing is that this final test set is a set of data that the AI has never seen before, so that you can do all of this training and then test it with something brand new and see how well it fares when trying to generalize to new information. Because if we're not careful, there are potential pitfalls that our AI can fall into if we're not careful about how we're going about training our neural network. And one potential danger is the danger of overfitting. So what does it mean to overfit? Well, when we overfit on data, on our training data in particular, we don't learn to generalize very well, and we really are just learning what the training data is telling us. So what do I mean by that? Well, let's take a look here at some example data. I have some red points around here, some blue points over here, and maybe I'm trying to learn a classification task. I want to be able to separate the red from the blue. Well, it seems like even though this data isn't perfect, it's a little bit messy, much like real data really is. It seems like the right way to classify would be something kind of like this. So it seems like the reds are generally in the lower left part of my screen. The blues are generally in the upper right part of the screen. Of course, it's not perfectly accurate. There are a few outliers, but that's the general idea. If we're not careful, though, AI might overfit on the data, and it might do something like this. That definitely does a good job of separating the red from the blue, but it's this kind of winding path that's very specific to just this particular data set, and it's probably not going to generalize very well if we're looking at data that's not part of this original data set instead. What I really want to do is learn something that's going to generalize no matter what data I'm looking at, even if it's data that doesn't really look like any of the training data that I have here to start with. And so that's one thing we have to keep in mind, one of the reasons why it's important to be thinking about what are you training your data on, what are you testing your data on. But then yeah, I'll go back and redo that example, I think. So let's take a look at some examples. Here's an example of some data. I have some red points and some blue points. And imagine that I'm trying to perform a classification task. I'm trying to separate the red from the blue. Well, it does seem like I could perform that classification by learning a boundary that looks something like this. It seems like the red points are generally in the lower left portion of my screen. The blue points are generally in the upper right portion of the screen. And so a line like this is approximately what I might be interested in learning. But of course, it's not perfect. There are some red points that fall on the blue side. There are some blue points that fall on the red side. So it's not perfectly accurate, but it does seem like it's going to be a generally good line for separating red from blue. But if I'm not careful about how I'm training my neural network, I might end up learning a boundary that looks something like this. Now, you might argue that this is a better boundary between the red and the blue because it does a perfect job of separating the red from the blue. All of the reds are on this side of the line. All of the blues are on that side of the line. But what we've run the risk of here is overfitting. We've very specifically designed this line to do a great job of separating red from blue for this particular data set, but it might not generalize so well to data in other data sets that we haven't seen before, because these are probably likely just outliers of this particular data set and maybe not representative of some general trends or general patterns. Now, if we had a lot more data and we did notice that they tended to follow this shape even further, that might be evidence that this is a better line. But in this case, it seems like we might have overfit on that data, and that would be something we'd want to check for. by testing our neural network with some data that we hadn't seen before, for example. One other consideration we need to take into account when looking at how it is that we're training AI on data like this is what data we're even using. Because whatever data we give to the AI, those are going to be the patterns that AI is going to learn how to process and deal with. And as a result, if there's any kind of bias in that data set, that bias is going to be reflected in the result of what the AI is actually learning. And we like to think of computers as these unbiased calculators that are always going to give us the right answer. But in particular, when it comes to neural networks, any of the biases that are in the data to begin with are going to end up showing up in the result of what the AI is learning how to do. So if we're training the AI to recognize images, but we're only using images from one country or from people that look a certain way or of a certain ethnicity, for example, then potentially we're not going to be doing a very good job of generalizing to types of data that weren't part of the training data, that weren't part of the kinds of data that were shown to the AI when it was learning. If there was a whole big sample of red points way up here that we just didn't include in the training data set because of the way that we collected the data and provided it to the AI, then it's potentially going to miss out on that too. So it's important as we're collecting data, providing it to the AI, that we're thinking about how to make sure that that data is representative, that we're really getting the full range of data that we might want the AI to be able to learn from, and that we're not missing out on part of the data that might be represented there as a result. And as we add more and more data, we're going to have to think about how it is the AI is able to train on that efficiently. Because the more data we have, the more and more training is going to be required, especially as our neural networks start growing longer in terms of having many more layers, many more inputs, different filters and convolutions that they're performing now. And if we think about the heart of the way a computer's computation works, much of the computer's computation happens in the central processing unit, or the CPU, at the heart of many computer computations. If you ask the computer to do some math or make a decision or move some data around, odds are it's going to be the central processing unit, or the CPU, that's doing just that. And now you could train a neural network using the CPU, but it's going to end up being fairly slow. CPUs historically could only do one thing at a time, although now many modern CPUs have multiple cores that allow it to do multiple things at the same time. But instead, we could use a different type of chip known as a graphics processing unit, or a GPU. And GPU can do much simpler types of computations, but the advantage is it can do many of them in parallel. And the nice thing about a neural network is that training a neural network often requires fairly simple calculations. As we've seen before, what a neural network is really doing is a lot of multiplying numbers together and adding numbers together, in particular in a very structured form with like grids of numbers with rows and columns. And that's something that a GPU is very, very good at because it can do those simple operations in parallel very, very quickly. And in more recent years, companies have developed specialized chips that are specialized for the very particular kinds of calculations that are specific to neural networks and deep learning as well. So the particular choice of hardware, too, can make a big difference in terms of how efficiently we're able to do this training. Now, how else might we try to make the training of our neural networks a little bit more efficient? Well, let's think about the way that you and I learn. When you and I learn something new, we often use our existing knowledge to help us learn a little bit more. If I teach you to recognize one kind of animal, you can use that information when you're trying to learn how to recognize a different kind of animal instead. But so far, in the context of computers and neural networks, they haven't really been able to do that. You train a neural network to do one thing, and if you want to get a neural network to do something else, you'll have to train it again. So now what we'd like to do is explore this idea of transfer learning, that if we teach the AI to do one thing, can we transfer that knowledge to something else? And so what might that look like? That might look like we train the AI to recognize one kind of animal, to be able to identify, is it this animal or that animal, maybe distinguish between a few different kinds of dogs. But if we then want to train an AI to be able to distinguish between different kinds of cats, how would we do that? Do we have to start from scratch? Or is there a way to use the knowledge we've already learned to be able to apply it to that new domain? And so here's how you might do that. Imagine you had a neural network that did something like identify different kinds of dogs. And so we started with input, the image of the dog, and the output was a classification between different kinds of dogs and whether we think it belongs to one of those categories. And in between are all of these hidden layers. And each hidden layer you can imagine doing something useful, performing some kind of useful transformation on the data, identifying fur, for example, or identifying the shape of the animal. And some of those things could be useful for identifying different kinds of cats too, and we might want to learn from that existing data, that existing training we've already done on this neural network. So what could we do? Well, what we could do is assume that these early layers are probably doing something useful that'll be useful for cats as well as dogs, not just dogs. We'll take this neural network, we'll get rid of this last layer, and we'll introduce a new final layer. And that new final layer will now be responsible for identifying different kinds of cats. And what we'll do is we'll now train the neural network to be able to use the same existing architecture, but just with a new final layer to be able to use the features that it's identified to now see if maybe it can do a better job of identifying cats as well. And how effective that is depends on whether or not these early layers have learned something useful that's going to help us in identifying whether something is a particular kind of cat. But it might actually end up being faster because we don't need to worry about retraining all of these earlier layers. The earlier layers have already learned something useful. We just need to think about what the later layers are doing in order to try to draw some conclusion about what the resulting kind of animal might actually be. And if we wanted to, as we go about training that new neural network, we could go back and adjust the weights of the earlier layers too. That maybe those earlier layers were specifically tuned to trying to identify particular features that were useful for dogs, but maybe by making some small adjustments to them, we can end up finding some features that are useful for cats too. Take a short break. So that process of taking an existing neural network, modifying the existing weights a little bit as we train it on new data to try and perform some new task, we call that fine-tuning, taking an existing machine learning model and making some adjustments to adapt it to a new task, which can often be more efficient than trying to train a new neural network from the very beginning. So those are some of the big ideas behind how we can use AI to process images. But images are only one form of sensory input that we take in when we're perceiving the world. Another common form of input we take in is that of sound. We can hear the world, we can hear people's speech and process it and figure out what to do with it. So what would it take for an AI to be able to process sound and to be able to understand what it hears and make some decisions based on that too? Well, to do that, we need to think about how sound is represented. And ultimately, sound comes in the form of waves, waves that look a little bit something like this. And sound exists at different frequencies. So when it's higher frequency, you'll see more of these peaks and valleys more frequently. For a lower frequency, it'll be sort of a slower, gradual rise and fall of the waves. But as far as the computer is concerned, we need to turn this wave into values that the computer is going to be able to understand. In other words, just numbers. And so here is a computerized version of how it might represent those waves. We've just divided into discrete units of time, where each unit in time, we're representing the value of that waveform. And so you can still see that the wave has that same kind of frequency, but we can now imagine representing each of these bars as just a number, representing the value of this audio waveform at that particular moment in time. Now, of course, in reality, the sounds we hear are usually not just one single pure frequency. It's going to be a mix of frequencies of different voices and sounds that you're being heard from different directions. And so it's going to look a little bit messier, as with the image data. It's not perfect. It's going to be a little bit messy. But what we might like to do is ultimately figure out how to take this data and transform it into what the frequencies actually are. Because if we know what the frequencies are, we can get a sense for how to interpret it. Because different sounds, different letters of the alphabet when pronounced will use different frequencies. And so ultimately being able to separate this into its frequencies is going to be a useful operation for us. And there is a mathematical operation that allows us to do that. That mathematical operation is called the fast Fourier transform. And what that does is it allows us to take a signal like this, a mix of a whole bunch of different frequencies, and separate it out into the individual audio frequencies, which we can often represent using something called a spectrogram. So what is a spectrogram? What does it look like? Well, here's the idea. We have a whole bunch of different frequencies, so low frequencies at the bottom, and then high frequencies at the top. And what a spectrogram is going to be is a visual representation of those frequencies. So here, the darker areas mean that we have some frequencies in the middle here that are more present, and then some upper, higher frequencies that are present as well. And then we'll repeat this across time. So for each unit of time, we'll have a slice of these frequencies. And so ultimately, if you're listening to audio over the period of a couple of seconds maybe, you'll end up with a spectrogram that looks a little something like this, where we have a time dimension here, so the beginning of the audio clip, the end of the audio here. And then we have all of the different frequencies with darker areas representing areas where their frequency happens to be more intense. So let me show you a real-world example. Earlier, before this lecture, I recorded myself saying the words artificial intelligence. Here's what that looks like as an audio waveform. So this is the audio waveform of my voice saying the words artificial intelligence. And by just looking at the waveform, it's a little bit difficult to figure out how to make sense of that information. Maybe you can tell that there are some louder sounds here, and then it trails off a little bit at the end. But knowing specifically what sounds I made, that's going to be a little more difficult. But by applying a fast Fourier transform, what we can then do is turn it into a spectrogram. So here's the actual spectrogram of my voice saying the words artificial intelligence. Here's the beginning of the audio. Here's the end of the audio. Then on the vertical axis, we have lower frequencies here and higher frequencies here. And now this form is a form that's a little bit easier to work with and identify. That you can imagine that vowels often have strong, very clear bars that show up in terms of particular frequencies that are particularly prominent. So at the beginning here, you can see a few bars here. That's the bar of the A in the word artificial. And so we have those bars that are visible there. And then there are a few bars here. That's the I in the word intelligence at the very beginning of the word. And there are other things that you might notice here. You notice that there is some darker bars here in this particular pattern in this section over here, which kind of are in similar places to the dark bar here and a few bars that appear above it a little bit later in the audio clip. That's the letter L at the end of artificial. That L at the end shows up here. And then in intelligence, that L, you can see those showing up here. This area here, where you have intelligence perspective, is that what you're looking at here is an image. It's an image with pixels. It's got rows and it's got columns. And you could take this same image and pass it into a convolutional neural network, just like we've been looking at before, that will be able to look at particular patches of this image and identify the kind of patterns we've just been talking about, to identify particular frequencies, particular sounds, to be able to understand what sounds are happening and what might be happening in sequence as we go from beginning to end across this piece of audio. It's a variety of different ways that computers can take this data and process it as audio to understand what it is that I might have said. So what we've looked at now are different ways that computers can deal with sensory information the way that we do. We see the world, we hear the world, and AI can do the same. And we're seeing AI start to get even more intelligent capabilities. And as we continue in the course, we're going to explore even more intelligent capabilities that computers have as we explore all of these possibilities in the fundamentals of artificial intelligence.